Welcome back to another lesson in MCV4U. Today we'll be looking at vectors as velocity. So if you recall, again, velocity is a vector quantity. It is a vector quantity with magnitude and direction. An example, velocity of 60 kilometers per hour at 60 degrees north of east. So that indicates, again, a direction. Speed, however, is a scalar quantity with just, again, the magnitude. So example, speed of 60 kilometers per hour. Here we see in terms of velocity vectors, the heading is the direction that you steer an object. So for example, a boat, a car, in order to end up in your intended bearing. Ground velocity is the velocity of an object relative to the ground. So ground velocity is velocity object relative to the ground. It is the resultant vector from two given vectors, the air velocity and wind, or current velocity. So again, air velocity and current velocity. So ground velocity does not mean traveling, again, along the ground. It just means that it is relative to the ground. So here we see that we're provided, again, an example, we have vector for air velocity, vector for wind and current velocity, and then we have our resultant vector, which is our ground velocity. And so here we see this example. It says an airplane is heading northwest at 500 kilometers per hour, encounters a wind of 125 kilometers per hour from 25 degrees north of east. Determine the resultant ground velocity of the plane. So here we're determining the resultant ground velocity, again, of the plane. So again, we need both the magnitude and the direction. Here again, we see here that it's 500 kilometers per hour. Again, wind of 125 kilometers per hour from 25 degrees north of east. So again, here we can write that it's coming from north of east. So here we can write as E 25 degrees N. And so here, what we want to do is we want to draw. So we want to draw the resultant. So we want to draw the resultant from the tail of the plane. The tail of the plane, velocity to the tip of the wind velocity. Okay, and here we know that if it's heading northwest, again, that means that it's going to be at 45 degrees. Okay, so here if we draw our diagram here, and here we'll label again our north, east, south, and west. And so here we see that we have our, again, our airplane here is heading, again, 500 kilometers per hour. we see here that it's at 45 degrees because it's heading northwest. Again, here we see then that it encounters a wind 125 kilometers per hour from 25 degrees north of east. So here we have 25 degrees and 125 kilometers. That is the wind velocity. And so here, and we can draw our wind vector again here as well. Again, this is 125, and the angle that gets created is. So here, if we connect it, again, this would also be 25 degrees, this angle here, and here. This is still 125. And so we can connect the resultant vector, again, which is from the tail of the plane velocity to the tip of the wind velocity. So okay, from tail to tip. And we see here that if this is, again, 25 degrees, then the angle that's inside would be 110 degrees. And that's because here, again, we see that 25 degrees, again, plus theta plus 45 degrees is equal to 180. And so here we see that theta is equal to 110 degrees. So here we see that here theta will be equal to 110 degrees. And so here, if we look at we're looking at our direction, again, we will label here, again, this entire thing, and here we'll label this angle as beta. And so if we're looking at, again, the direction of the resultant, again, it would be north 45 plus beta degrees west, or if we see it from west, it would be 45 minus beta degrees north. So here first we'll find our magnitude of the resultant. So here we have r squared is equal to 500 squared, again here we're using cosine law again, plus 125 squared minus 2 times 500 times 125 cos of 110 degrees. Here we get that our magnitude of our resultant vector is going to be equal to 555.3 kilometers per hour. So here we have to find our beta. So here we'll use sine law. So then here we have sine beta over 125 is equal to sine 110 over the value that we just found for the resultant, which was 555.3. Therefore, we see that beta is equal to 12 degrees. So here, therefore, the ground velocity is 555.3 kilometers per hour, 57 degrees north of west. Okay, so let's look at the second example here. So it says the plane is heading 70 degrees south of west, again with a ground speed. Okay, so that means that's going to be, again, our resultant vector of 625 kilometers per hour. If the pilot is steering west at an airspeed, so again, that's going to be the velocity of the plane. So again, that's going to be the velocity of the plane of 665 kilometers per hour. What must be the wind speed and wind direction? So here, again, we'll draw our diagram. Here, north, east, south, and west in terms of our direction. So here, again, the plane is heading, again, 70 degrees south of west. And so here, if we draw this, so here, this will be our 70 degrees, which means that this angle, again, 90 minus 70 here, this will be 20 degrees. Again, that is heading a ground speed of 625 kilometers per hour. And here, again, we see that, again, if the pilot is steering west at an airspeed of 665 kilometers per hour, draw that as well here. So this would be 665. And then here, again, we're looking at the wind speed, or vector W here. Okay, so here, if we look at, we draw another, again, plane here, again, looking at, again, the direction. So if we see north, east, south, and west. And here, when we look at our angle, theta, we see here that, again, the wind direction will be east, and whatever the theta degree is of south. Okay, so first we'll find the magnitude. Again, so here we have W squared is equal to 665 squared plus 625 squared minus 2 times 665 times 625 post 20 degrees. And so here we see that our magnitude for vector W is equal to 227.5 kilometers per hour. Here, then we'll find our direction. So here we have sine theta over 625 is equal to sine 20 over 227.5. So here we see that theta is equal to 70 degrees. So here we can see that therefore the wind vector is 227.5 kilometers per hour and 70 degrees east of south. In example number 3, it says a canoeist who paddle at a speed of 5 kilometers per hour in still water wishes to cross a river that is 400 meters wide and has a current of 2 kilometers moving east. If she steers the canoe in a direction perpendicular to the current, first determine the resultant velocity, express direction as an angle from neutral position, and then find the point of the opposite bank where the canoe hits the shore. So here we'll draw our diagram. Again, here we'll draw our river. And here, again, we have in this point here. So again, the canoes can paddle at a speed of 5 kilometers in still water. So 5 kilometers in still water. And we get, again, crosses a river that is 400 meters. So from here to here, this is 400 meters. And here we see that again, there's the wind direction that's current of 2 kilometers per hour. And that is heading again. Again, that has a wind of 2 kilometers per hour. And again, we have our resultant vector here, and then our theta, which is our angle. Again, this being the neutral position. Okay, so here, to find again r, we'll use our Pythagorean theorem. So here we have r squared is equal to 2 squared plus 5 squared. And so the magnitude of r is equal to 5.4 kilometers per hour. Here to find our angle, we're going to use tangent theta is equal to 2 over 5. Theta is equal to tangent -1 of 2 over 5. And theta is equal to 22 degrees. And so here it says, again, find the point on the opposite bank where the canoe hits the shore. So here that would be our value up here. And so here for part B, you see we can calculate that using tangent 22 degrees is equal to x over 400. So here we see that x is equal to 162 meters. And so we'll do our therefore statements. So again, for firstly, the resultant velocity is 5.4 kilometers per hour, and then 22 degrees downstream with the current. And here we see that for part B, again, the point on the opposite bank where the canoe hits the shore. And so therefore the canoe hits the shore at 162 meters. Okay, in example 4, it says suppose the canoeist in example 3 had wished to travel straight across the river. Determine the direction she must head at the time and the time that it would take her to cross the river. Okay, so again, we'll just draw our river here. And we know that it is 400 meters across. Here we'll look at our again, velocities and our vectors. Here, this would be 5. This is 2, which was again the wind vector. And then now we're looking at do you want to go straight across the river? And so again, and we're looking for the speed here. So again, here we have our theta. And again, we look here, and the direction is relative to the bank. So here to find again our speed vector, which is our resultant here, again, we have r squared plus 2 squared is equal to 5 squared. And so here the resultant vector is equal to 4.6 kilometers per hour is our speed there. And again, if we find our direction, here we can use sine theta is equal to 2 over 5, and theta will be equal to 24 degrees. And so again, the resultant velocity here, so the resultant velocity is 4.6 kilometers per hour, 24 degrees against the current, which is upstream here. So here again, we can take again our values. And so again, it's telling us to find the, again, the direction again, and then the time it must take for her to cross the river. So here we know that time is equal to distance over speed. So our distance, we take our 400 meters, we're going to convert it to kilometers, which will be 0.4. So it'll be 0.4 over the speed, which was 4.6. And so that's equal to 0.09 hours. And here, if we multiply that by 60, get that into minutes, again, is equal to 5.4 So 5 minutes, then we take our 0.4 and multiply it by 60 seconds, which will equal 224 seconds. So again here, therefore, it takes 5 minutes and 24 seconds to cross the river.